Wonderful. So, well, good afternoon from my side too. Glad to be here. Thanks for the invite. And I thought when I was invited, what is actually hot topics in solar thermal technology right now? And from maybe the media, you have been already seeing that PVT is a hot topic right now. And so I decided to bring you something about PVT. And as it is really, let's say, cutting edge technology-wise, but also market-wise, there is ongoing projects in this field of solar thermal and photovoltaic energy conversion technologies. And therefore, I decided to bring you some insights from a still running research project. So the slides I will share with you are really output which we are also sharing just recently with our project partners. So it's really very recent development. For that reason, also please excuse, I tried to translate as many of the slides as possible. It's a German-funded research project. Most of the slides were in German. Some I did not translate, especially in the graphics, but I will explain it in English. So with this said, I want to introduce you to the project Integrate. Integrate has a long German title from which the abbreviation is derived. I will not bother you with that, but it is a project which brings together the photovoltaic thermal technology, PVT, with heat pumps and other potential market entrance technologies, and does monitoring, simulation, and marketing for the technology. Marketing in the real understanding of the word. So it's not about advertisement, but it's about marketing. So preparing the markets with all the necessary information so that a well-informed buying decision can be fostered. So this is the basic background, and maybe I start with at least a few slides on the technical background, what a PVT is. I was not very sure how clear that is to the audience. So here you see the solar spectrum over the wavelengths. On the x-axis, the wavelengths, the intensity of the radiation on the y-axis. And you see that there is a blue area, and it is indicated with around 18%. That is, just try to get me my pointer. That is the silicon-based conversion rate for silicon-based photovoltaics. That's the conversion rate for silicon-based photovoltaics. And so this is kind of limited. And you see there's a lot of rest energy which is available in the solar spectrum. The gray, dark gray area is some optical losses, which you always will have when you come from different densities, like air to glass or air to polymers. You will always have some optical losses on these surfaces. And then the yellow part here in a photovoltaic cell is called heat loss, because it is converted energy. Photons are converted, but they are not converted into electricity as the blue part down here, but into long wave radiation, infrared radiation, and so-called heat. And this heat is lost. There's even a disadvantageous effect that the photovoltaics, silicon-based photovoltaics, reduce their efficiency the hotter they are. So this waste heat is heating up the modules, the cells, and by that actually even reduces the efficiency. So now you can easily understand, to have the idea that these heat losses, if we convert them into heat gains by converting them in a way that we make this heat usable, is a big plus. We, first of all, take this energy into account and make it useful energy. And as a second side effect, we even prevent the overheating of the module a little bit. So first thing to understand, PVT, photovoltaic-thermal technology, is one product which on the space area it covers converts photons into electricity and heat in parallel. And by doing so has a very good area-specific conversion rate. And the mentioned benefits appear. And one thing which I directly want to mention here too is heat and electricity are very different forms of energy. Electricity, you might be familiar with the concept of exergy, is basically exergy, so you can convert it into almost any other energy form, while heat, the value of heat is basically measured by the grade of the heat. So how hot is the heat? And by the heat level, the heat grade, you can convert it maybe by thermodynamic machines into other forms of energy. So there is a big basic principle difference in heat and electricity, and this will be very important for the following when we look into the applications of these PVT collectors. If you take this physical principle and make it a technical principle, then you can see here a very schematic cut through such a PVT collector. I look into it with you step by step. We have a frame which holds everything together. And then within the frame, we have a layout of an absorber or module. And normally that starts with a PV module glass, might be a polymer as well. Then a embedding material which positions and holds in position the cells. In many modern modules, this is EVA, but there is alternatives too. Then there is a backside sheet, and this has typically a Tedlar foil in it, and then an adhesive, which maybe be attached to a metal sheet. And this metal sheet transfers the heat away from this absorber layout to these tubes, which are flown through by a fluid, which then transports the heat from the roof or from the PVT collector to the heat sink. Heat sink in many cases might be a heat storage, but sometimes also a different direct use of that heat. And then there might be an backside isolation, which reduces the thermal losses to the backside. There is a lot of different variations of PVT collectors. And so this schematic just shows the different layers in principle, but not every product, not every PVT product will have all of the layers. For example, there's a lot of non-backside isolated collectors. Just saying, I hear somebody talking, which is not a problem for me, but if you really want to talk to me, please talk loud and clear, because I don't see anything else but my presentation. So if you want to ask a question or something, just address me clearly, maybe, then I'm happy to help. There is some challenges in the construction of those products. On the one hand side, you want a very good thermal coupling of the cell material to the fluid. We understood that already from the physics, that this cooling of the cells only works if you really take away the heat from the cells, obviously. Then also you want to run at maybe a potentially high grade heat, because that is a value. So you want to minimize your heat losses, but you still want to have a high electrical efficiency. And as I said, silicon reduces efficiency the warmer it gets. So we have kind of a competing optimization problem here. And then, of course, as with all of those products, the durability of the used materials is essential. We are building for a sustainable future. We are having renewable energies. We want to have very durable products, and in the best case, in the end, after a long lifetime, recyclability is also not an issue, but a thing to consider. And as you can see, we have several layers of different materials, so that is something to consider. Okay, so now we understood the basic physics, how it in a technical version can look like. Now let's look at the modes of operation. It's a little bit a complicated graph, so we will spend some minutes on it. I hope, I guess you all are kind of familiar with solar thermal energy conversion technology, where purely the heat production is the goal and is done very efficient. With PVT collectors looking at the thermal part of energy generation, we have a different situation. The y-axis indicated with the black bar here shows you the heat gains just in quality, and the x-axis shows you a classic way of showing that. It's the delta T between the fluid temperature, fluid mean temperature, and the ambient temperature. So how much energy you basically overheat, or how much temperature you overheat the fluid. In this very right graph, quant 3, the operating temperature is above ambient temperature. We have solar radiation. We are running the product rather like a solar thermal collector would also operate. And we provide this heat to our system. The red curve, by the way, is with solar radiation, while the blue curve, which I will explain in some minutes, is without solar radiation. But first, back to the solar radiation curve. This area, higher than ambient temperature, fluid temperature is higher than ambient temperature. So we have basically some losses to the ambient, but we have a lot of solar radiation, so we still make a lot of winds and we can heat up our fluid. When the solar radiation goes into an area where it's slower, the operating temperature might get close to ambient temperature. And at some point, it might be under ambient temperature. So now a specific effect happens. As the ambient is warmer than the fluid, ambient energy can be absorbed into the fluid. And we will later see that there is products which emphasize this operation mode by having a big heat exchanger area available to the ambient air. So all of a sudden, we have more than one heat source, not only solar radiation, but also ambient heat. Last but not least, when you go to the very left, which means at some point, if you cool down the fluid you run through the collectors more and more and more, then there is a dew point when the humidity of the air starts to condensate on such a cold surface. And if you cool it even further down, at some point there would be a freeze point where this humidity would start frosting on your surface. The frost would kind of isolate, so that's why this is indicated as a rather flat curve. Okay, so this is the operation mode for the red line, and a quick look on the blue line too. no solar radiation available. First of all, on the very right, here in the negative part of the operation mode, you can reject heat. So you would run warmer fluid than the ambient through the collector, and by having a heat exchanger to the ambient by radiation or convection, this is rejecting heat, cooling. Many of you might come from countries also where cooling need in buildings is actually almost bigger or same as heating needs for the buildings. So you can easily understand that rejecting heat sometimes can be very interesting as a technical operation mode. Then in the middle, we are harvesting energy from the ambient temperature, but we have no solar radiation. So this is, for example, at night, no radiation available, but we still harvest energy from the ambient. And then to the very left, same as I already explained. First of all, coming close to dew point, then from dew point to freeze point, and kind of stopping the heat exchange by that. Okay, so to sum it up, we're utilizing two energy sources, ambient air and solar energy. We have new effects to consider, condensation and icing. And because of the very low graded temperature which we might harvest, we have to look if and when this temperature actually is useful energy to us. And that is when the heat pump comes into play. And I will explain a little bit more, or let's explain it here. The heat pump as a not really energy, let's say, providing technology, but energy enhancing technology is pumping heat from a low heat temperature level to our use heat temperature level by investing electric energy. So a heat pump is basically a reverse fridge. So it pumps from a low temperature level to a high temperature level. And for that pumping process by compression technology, for example, it uses electricity. So here you can see this low graded heat can be a source for the heat pump. And by that combination, we will actually provide our useful heat by a very good conversion rate on the heat side as a source, then hopefully a very efficient heat pump with a little bit of electricity to our useful heat. We will see that later in the applications several times. I started saying, excuse me, that the PVT collectors look very different, and these basic principles are now understood. If you look at the temperature range those PVTs are operated in, you can see that we start even way below ambient temperature, or not below, at low ambient temperatures, -10. But we also have an open end more or less, but let's, for the graph, we decided to limit it here to 120. So there is, for example, concentrating PVT collectors, which would directly provide temperature at a temperature level of 120. You have to think back or remember on the second slide, the challenge to make electricity output and thermal output both effective, and also the durability of the materials. If we're talking about those kinds of products, it's typically not a standard PV module anymore. It's very engineered cell technology. Embedding materials are engineered to these cases. While at the lower end, here these so-called uncovered PVT collectors or whisk collectors really are kind of standard PV modules which are enabled by a heat exchanger to be a PVT. And you will find everything in between. And you also have in the top here the applications indicated by those products. So the main takeaway from this slide is, if you know your application, you can choose what kind of technology PVT is the fitting one for your case. And there is also kind of no-goes. You will never provide swimming pool heating with a concentrating PVT collector, and it's really hard to provide with an uncovered PVT collector process heat if you not have a very special process or you put a heat pump in between. Just to illustrate that a little bit, here you see real products and you see how different they can look. Evacuated tubular PVT collector here in a rendering for a hotel in Frankfurt. Here, South Africa, Cape Town, a concentrating PVT collector. Here, a let's say, flat roof integrated PVT array for a multifamily house, and as well as here in a renovation situation that was a smaller building which got a lot of extra floor and new roof and balconies and whatnot, and also a new heating system. And here it's also a PVT based heating system. What I also wanted to share with you from this project I opened with is that we do technical monitoring. And when such a new technology enters the market, of course, there's a lot of questions. How much does the kilowatt hour heat cost from such a system, electricity cost from such a system? How durable is it? How reliable is it? Does it work at all? Can it fulfill the needs of comfort in every minute of a year? In which situations does it work? And so on and so on. So the technical monitoring is an essential part of answering those questions. And here you see a lot of different buildings, refurbishments, new builds, bigger, smaller, semi-detached, single-family homes, and so on. And we did a monitoring on those. And I have to speed up a little bit, I see, but no problem. I will still get the main points. The way you want to compare with the existing market is so-called KPIs, key performance indicators. You have existing solutions to provide heat and electricity, and now you come up with a new inventive solution. So you have to compare your product against the market, and you do that on these KPIs. And one KPI for heat pump systems is the seasonal performance factor. So it's kind of a measure for the full year through efficiency of your heat pump. This kind of base definition is seasonal performance factor is the heat energy you harvested and provided to the system divided by the electricity you used, the electricity effort you had to use to make this happen. And that is what we also chose for our monitoring. And you see here the boundaries indicated in the green and red squares. Heat provided to the tap water, heat provided to the heating system, divided by the electricity necessary to generate that heat. So, for example, in one of those cases, we had 13,000 flat kilowatt hours thermal per year delivered with a intake of around 4,000 kilowatt electrical energy. So this results to a yearly seasonal performance factor Jahresarbeitszahl of 3.3. And sometimes this is done, and as I said, the technology is new, so there's no real standard around that yet. Sometimes people argue that some of the PV electricity you get from your PVT is directly used for running the heat pump. And so you don't have that as a load on the grid. And that is kind of a value itself. And so they subtract the kilowatt hours of electricity which you can directly use from this necessary electricity from the grid. And as you can see, if you subtract something down here, then your seasonal performance factor gets bigger. So in this case, if we would do that, we could show that around 1,000 kilowatt hours the PV electricity could directly be used, and then the seasonal performance factor would even go up to 4.4. So my message to you on that is, be careful when you see different of those values, and ask yourself or ask the provider of those values, did you subtract that or did you not? Because otherwise you're really comparing apples with pears. I have some excerpt of those houses I showed you before now for the seasonal performance factors here for you. It's again because of the comparability. Some of the houses were very specific in their operation. So here we have kind of a set of houses where, yeah, it's legitimated to compare. And you see that they are sorted by the seasonal performance factors, highest here by 4.2, and then going down to 3.4. It's 2 years in a row for most of them. 21 is the lighter gray, 22 is the darker gray. So one thing which is interesting for a new technology, that we had rather constant performance over 2 years. And yes, there were some optimization after the first year. You learn a lot when you do such a technical monitoring, and then of course you adjust your control strategy or even your hydraulic connections and so on. So it helped to do the monitoring to improve, but also it shows that these technologies are rather stable already, or these solutions, these systems are rather stable. And I couldn't provide that for today, but the year 23 is still in the monitoring, and it's also evaluated now, and it's stable again. So what we can say is it is working, yeah, and it's working over several years, and that by almost the same values. That is already a good message. And now, of course, we can look into that a little bit more in detail. I skipped that to save some time, but when we take, for example, this house here in Sweden, it's a single family home in this case, quite some area of a heating area, 340 square meter. They had already a borehole and a heat pump, but the borehole was cooling off over many years, and she was extracted, and so the ground cooled down, and it was even more and more complicated for the heat pump to extract enough source energy. So they had to do something. They did not want to drill again, also for the costs. And so they came across PVT as a technology and decided to put 90 square meters of PVT on their roof. They bought a bigger heat pump, 11K kilowatt, and so added a second source to the already existing but cooled out ground source. This is connected to a heating system and a tap water system. So what happens here? In this graph, you see January to December, a year, and you have a positive and a negative energy on the y-axis. The months where you have a lot of solar radiation, they use the heat from the PVT field directly with the heat pump to provide the tap water temperature. But that is not a lot. And so there's a lot of excess energy. And this excess energy is pumped down into the ground using the existing boreholes and kind of using the ground as a seasonal energy storage, if you want to call it like that, or regenerating the borehole. At night, even in summer, there's obviously no heat directly from the PVT field. That's why you see still a brown bar positive energy takeout from the ground, even in summer, but smaller than, of course, in winter, where you have also direct solar contribution, but then a way bigger share from the borehole. And you have no excess. It's directly used if you have, so no excess solar energy to recharge the borehole recharging only through the summer months. But by doing this combination, you could avoid extra drilling, which is a lot of costs, and you have a very functional system. For the whole year, you see the energy consumption was something like 25% electricity to provide the full heating. And the heating had 15% directly from the PVT field, 44% directly from the ground, and 16% basically through the PVT field from the ground. So a recharging load. Let's look into a second installation for today, just to show the potential of this technology. Here we have a house which is way smaller. It is rather modern, so it has an underfloor heating system. So it can run the heating system on lower temperatures, which is helpful for renewables. It still has a heat pump as a main heating enabler, but it also has a 7 kilowatt direct electrical rod heater. On the roof, we find a 16 square meter PVT collector. And what you see in the schematic here is that the PVT collector is the only source for the heat pump. So here is no ambient air heat exchanger as you would normally expect for a heat pump. These vents which are put somewhere at the fence and run to extract energy from the ambient, or the ground holes as we just saw in the example before. So we don't have that. The PVT collector is the monovalent source for the heat pump. So question is, does that also work? Answer, yes. And I show you how. Kilowatt hours again on the y-axis, year January through December on the x-axis. You see in red the tap water demand in dark red and the heating demand in lighter red. Obviously in winter in Central Europe, you have heating in winter months and in summer rather not. And then you see in black and gray the electricity used for that. The dark, or the black is the heating rod. So it's really direct electric heating. And the gray is the heating by the heat pump, which still uses some electricity to run. And then you can calculate in these dots a monthly performance factor. And you can see that we had also some interesting artifacts, like here in August. You see that there is direct rod heating in August. That is, for example, a good reason to call the operator and say like, something is not optimum in your control strategy. You should be able to run this just directly via the heat pump and so on. So, but you see that overall, yes, there is also some direct heating rod necessary. Obviously, here was maybe a long, cold week. If you remember 22, I don't know who of you were in Germany at that time. but it was just before Christmas for 14 days at -10 degrees and rather foggy. So that is obviously a period where you needed then an extra heating rod. But for the rest, the heat pump basically did the job. Skip that to leave us a little bit more time for discussion. And one of the last slides, now we see the performance, we see these key performance indicators. And as I started, you want to compare such a new technology, your innovation against the existing market. So that's what is on this slide. In brown dots and the brown tendency line, you see also monitoring, so meaning field measurement results for borehole heat pumps, ground heat pumps, and blue dots and blue trend line for air heat pumps. This was the ventilation unit. And our 5 houses are just now put into the same schematic, calculated to the same kind of reference temperature. And then you can see they are in between. Some are even better than ground hole heat pumps. Some of the air heat pumps are also as good as ground source heat pumps. So what is our takeaway? Obviously, it depends on who is installing the system, let's say, how suitable is the design of the system to the needs and the usage of the people living in the house. And the PVT-based heating systems are in between, but on par with the existing solutions. And this is a very encouraging result because it's an early phase of this technology. There's still a lot of things to optimize. There's still a lot of things to learn. And that this technology already is so competitive in the performance is very encouraging. So to wrap it up, there is quite some good thermal harvesting from a PVT collector, 300 to 600 kilowatt hours per square meter a year. That's a very good value. Electrical as well. It's a little bit better, let's say, as a standard PV, but in the same range. The coefficients of performance, I showed you a lot, I skipped that here, is on par to existing technologies. A question always arising is like, how much of the PV electricity can I actually use in my system, self-consumption? If you don't have a battery system, then this might be between 10 and 30% max. That is a matter of the simultaneous need and conversion. In winter, there's just not so much electricity also from your PV system available, but in winter, it's the longest hours the heat pump is running. But if you use a battery system, then you can push that to up to 25 to 40%. Of course, in theory, you can push it even higher, but most likely the economics will not allow for that. It will be very costly to do that. And a very important takeaway, PVT as a single source for heat pumps is a working dream team. Some extra reasons why this is a technology we will all see in the market in the coming years more and more. It doesn't emit any noise, so it's silent, which is in urban context a very important quality aspect. It is very area efficient because it converts electricity and heat and makes the most of your space. That's why the title of the presentation. And it can look very uniform, also an aesthetic argument for the installation, because it's just for a layman from down the street, it looks like a photovoltaic installation. If you want more information, feel free to go back in the recording of this, and you find here in the web a lot of free to use information. And with that, I thank you for your attention, and I'm hoping we still have some minutes to discuss some questions.
Yeah, thank you very much for your presentation. Yeah, definitely, we still have time for discussion. So if anyone has any questions, you can either unmute yourself and ask your question directly, and you're also welcome to ask it in the chat box. Here we have a question from Hector. He says, thank you very much for the presentation. And what tools can be used to model such systems, particularly for accounting the PV performance based on the operating temperature of the module?
Yeah, there is, let's say, different levels of simulation and design tools. Of course, for researchers who want to study the details of different layouts and so on, typically transit models are used. But for the end consumer market, there is commercial software such like TSOL or Polysun, which implement PVT collectors already in their latest releases. And so you can, for example, Polysun, you can per drag and drop take the most market available PVTs and just drag and drop it into your simulation and calculate for the output. But that's commercial software. So if you want to play around a little bit with that, go to this homepage you see on my last slide, pvt-energy.de. Oh, sorry, there's a big mistake. Don't do www. before that. It's an HTTP site, so leave the www away, just type pvt-energy.de. Then you will end up on the homepage of the project, and within the next days, it was just the go live of a simulation tool free of use, which we are hosting on that homepage. And in the coming few days, this link will be also available. They're literally right now working on it to put the link online. The IT team takes some time, but the software is programmed, it's ready, and that is an easy accessible first design tool, let's say, to play around a little bit.
Perfect, thank you. Hector, if you have any follow-up questions, you're welcome to ask them. Here we also have a question from Yasmin. She says, what's the average lifetime of PVT systems?
A little early to answer that question profoundly, but the basic idea is that the aging of photovoltaic modules is depending on some stress factors, and heat is one of it, not the only one. That heat, at least, we reduce by making it a PVT, because for some operating hours per year, we cool the PV down, so it's less hot. So we could assume that by this effect, we rather prolong the lifetime. Other things, obviously, if we run it at higher temperatures, remember this temperature block diagram, if we run it at higher temperatures and we, for that reason, change materials, we have to ask ourselves this question: new materials need new research on their lifetime. So it's a little bit tricky to answer for all the different variations of PVT systems, but I would say for a low temperature heat source for heat pump coupled PVT module, you can assume the same plus lifetime than for a PV module.
We have quite a few questions here, as well as appreciation for the presentation as well. And one question from Mohammed is, how much is the performance of panel expected from panels using PVT technology?
Okay, so I think the direct comparison, electricity output PV versus PVT, similar, the logic is similar. The PV is not hindered by the functionality of PVT. It is rather, if there is an effect, then it's a positive effect, because the PV itself could get warm if it's not ventilated well, if it's integrated, or if it's run in a country, for example, where it's very warm, then the silicon efficiency goes down. By taking this heat away for at least several hours a year, you rather harvest more electricity. You can say that in an European average installation where the temperatures are not that high, you can expect something by like 5% more electricity from a PVT installation over a pure PV installation. In a country like Saudi Arabia, as a big, let's say, ground-mounted field, you could actually rise your electricity output rather more, because there a cooling effect is way more important.
Yeah, we also have a question here on ground-mounted farms. The question is this technology suitable for large scales ground-mounted farms, as you said, and has this been already implemented?
Very good question. And at the edge, I would say, there is some first installations. And yes, basically it's suitable. And now in brackets, if you go ground mounted with a hydraulic system, you want to reduce normally the connections, because there's a statistic. If you have like a big field and every 2 square meters, you have to connect twice a hydraulic system, and a big field, you have thousands of hydraulic connectors, and statistically, one of them will always leak, and that you don't want. So the products which would be very suitable for big ground-mounted farms should be designed for it. And we don't have that on the market right now. So we don't have, let's say, big pre-mounted PVT modules which come, let's say, by crane and being put into the field, as we have for solar thermal installations. Maybe you had that in mind. Solar thermal installations, like in Denmark, but also in other countries, the single module is something like 20 square meters, and it's not carried up a roof, obviously. It is brought by a crane, and it's more an industrialized installation process. And I think that will be the tendency we will also see for PVT. So basically, yes, it's suitable. The products we have right now on the market, not optimized for it.
Okay, clear. Here, I think we have one final question from Invo, and he's asking how much has PVT been commercialized for now, and what would be the reason challenging it to be commercialized, and is there an attempt to make it BIPV?
Okay, 3 very good questions. Let me answer as quick as I can. Find the market report, which is published every year. It's called Solar Thermal Worldwide. No, Solar Heat Worldwide. Solar Heat Worldwide. It's free of charge. It's published by the IEA, International Energy Agency, and it has also the category of PVT in the market numbers. And roughly, PVT in Germany has now a cumulated installation of 150,000 square meters. Last year, a plus of 20, which equal to something like 126% market growth. So this is why it's a hot topic, because if investors see something growing with 126%, they all get dollar bills in their eyes. And so we are in a niche market. We are in an early phase. Of course, growth rates are big. But yes, this is a technology where I'm very confident that we will see it more in the coming years. So yes, it is commercialized, but there's room. More details in this market survey. Building integrated PVT absolutely makes or has potential, I would say. Again, there is at least one company I know of who wants to release within this year a building integrated PVT solution. It's tricky because you're interacting as a building product with a lot of regulations. So you're a photovoltaic module, you're a solar thermal collector, you're a source for a heat pump, and you're a part of the building envelope. This is the hell for the market entrance, quality assurance and testing and the verification and so on. So yes, good idea. Technically speaking, good idea. Lots of potential. Market-wise, a thick hole to drill. Can you say that in English? I don't know. It's a German element.
Could be. I also wrote the market survey title here for anyone to check. And Mominul, yeah, you're welcome to unmute yourself and ask a question.
Hi, thanks, Dr. Kramer, for the nice presentation and nice idea. My name is Mominul from Flensburg. I have a question that since you are showing all the examples with heat pump, is it possible to combine the financing of the PV module and heat pump and apply for subsidies together? Is there any policy?
Good question. Thank you for that. And yes, indeed, as you indicated almost, at the moment in Germany, subsidy schemes are regional, local, right? So I can only answer profoundly for Germany. At the moment, it is often, or if it is installed in combination with a heat pump, it's considered a part of the heat pump. And as such, it is part of the subsidy scheme and will be subsidized with the same quota as the heat pump is subsidized. So namely 35 to 45% with a cap at 30,000 per house and so on and so on. There's a lot of side rules in that, but basically it is a very, very good situation. It's a high subsidy also behind that technology.
Thank you.
Perfect. We have room for one last question, last 2 minutes, and a question from Courtois. Are there already LCOE comparisons of this technology versus conventional PV?
I see. It's you're asking really the right questions. Thank you for that. It is undergo. It is in process. One tricky question here is you're producing with the same investment 2 different forms of energy, electricity and heat. So LCOE, levelized costs of heat, levelized cost of electricity, take the investment costs plus maintenance costs, maybe soon plus recycling costs. That's still future, not done yet, and divide it by the energy delivered. And in this case, you have to kind of make up what ratio of the investment costs do you account for the electricity and what ratio do you account for the heat. Accounting everything for both would be unfair and disadvantaged. Accounting it only on one side is a bias. So it's not so easy to calculate. The principal calculation is available, but there is still ongoing research to find a guideline, a compromise, a standard maybe even, where everybody agrees that's the way how to calculate. And just to add a little bit more complexity layer, as the question before you just mentioned, subsidy schemes. In subsidy schemes, there's a differentiation that for the electricity, as there is a feed-in tariff, you cannot pay an investment subsidy. So for the subsidy, you also have to separate the investment costs into a ratio which was necessary for the thermal part and the ratio which was invested for the electrical part. And on the electrical part, you will not get a subsidy on investment because you already get the feed-in tariff. And there is a rule that you cannot double subsidize the same good, which also makes a lot of sense, right? So there's contradicting interests. If the market wants the most money, then they want to calculate their costs in an adventurous way for subsidy, but they also don't want to lose a customer by calculating, for example, the heat very expensive, because then the customer would say, this is in comparison to gas way too expensive. I don't want to buy that. So if you look close enough, the question of comparing costs is super tricky, and that's why it's still a matter of research, but there will be a solution soon.
Thank you very much for your answers. Fortunately, we came to the end of the talk, but again, thank you, Dr. Kramer, for your time and for your presentation, and to everyone as well for your engagement and